A little over 100 years ago, Albert Einstein first devised the general theory of relativity, describing nature as an interaction between space and time. Gravity is not so much a force, but something that curves space and time. But it has a few peculiarities. And one of those is that there can be waves in gravity. In 2015, for the first time, physicists were able to measure this. That sounds easy. It isn't. And one of the major obstacles is that you have to isolate all noise from the environment. Still, the signals are relatively weak. This means that you have to make a model of the signal and compare that against the data. Only then you can measure the signal that you're looking for. In principle, of course, you could simply try all possibilities, right? And in theory, that would work, of course. But you would need so many templates of all these theoretical signals that there are not enough computers in the world to do that, ever. So you need to do something slightly more clever. So there are some approaches to doing this. One of those is polynomial search. And that's actually what my thesis is about. So polynomial search is a technique that was developed at Nikhef by Henk Jan Bulte and Sipo van der Putte. And I have further developed this method over the course of this PhD research. What polynomial search does is it makes templates using what we call the Taylor approximation. Everything that you can describe with a mathematical equation can be approximated to some extent by saying it's like it is now, but it's changing linearly. And if you want to do it a bit better, then you can do it quadratically. So it also has a parabola component. And if you do it a bit better with a third order, you also have a third order account, which goes like this. And this is a way you can actually approximate any function to a certain extent for a certain piece of time. The nice thing is you only have these three parameters, right? You have the first order, second order, third order coefficient. So you can compute templates in a grid that matches these three dimensions. There are two topics in my thesis that are really new. I've participated in what we call the mock data challenge. So in total, 100 signals were hidden in the data. And it turned out one of the methods was even able to find all of them. And a few methods found some of them. And polynomial search was only able to find a few, unfortunately. But what was nice about this is that it confirmed that polynomial search is able to find signals that were injected into the data by an independent party. If you want to know that whether your method works, one of the ways is, of course, to look at actual data from the actual gravitational wave observatories. So in the sample analysis, I looked at 3 days of data from the Virgo gravitational wave observatory in Italy. Yeah, so what we learned is that it works. That's really nice. The nice thing about polynomial search is that it makes very few assumptions. So suppose we don't really understand what the signal looks like, or suppose that there are effects that we don't currently assess, then polynomial search will be able to find such signals if it's strong enough. So it really complements the suite of methods that we have to find continuous signals in the data.